All right, guys, welcome to another episode of Cuda Education. This is the Vulkan API series. We're talking about fences in the triangle.cpp algorithm. Shout out to Sascha Willems for creating these examples. It's a freely available algorithm on GitHub. His version is slightly different from mine because he actively updates his scripts, but the principles are the same, okay? If you want to join in on the fun, if you have a Windows-based machine with a Vulkan-capable GPU, Windows-based machine, Vulkan-capable GPU, you could get tutorial number 1, which is installing the Vulkan API on your machine, and tutorial number 13, which is installing a bunch of examples like this one um, on your machine. So you could run the examples and then learn Vulkan through tinkering with the code and learning the spec and all that stuff, right? Um, so let's get into it. We're talking about fences. Now, 2 videos ago in the whiteboard edition, where I was diagramming everything out, fences are synchronization between the CPU and the GPU, right? 2 different kind of items on your computing system, and they have to synchronize and communicate, right? So you have one process on the CPU, have another process on the GPU, and they both have to kind of be in sync with each other. So in our case, for this triangle algorithm, the CPU issues a draw call, the GPU does the draw, in other words, draws a triangle, and then it returns back to the CPU, notifying it that, hey, I've completed the draw. All right. So let's get into it. We're just gonna look up fences in the algorithm. So we have fences here used to check completion of queue operations. Example, command buffer execution. So we have a simple variable here called wait fences, and it is a vector type with type variable vk fence. All right, nothing special, a simple variable. All right, then we destroy stuff, right? Because we have the destructor here and we're destroying variables that we create, right? Good housekeeping. All right, next thing, prepare synchronization primitive. All right, so we said we have our fences here used to check draw command buffer completion. So we have our create info situation here, typical Vulkan stuff where you outline a bunch of options and parameters and things that you want. And then in the call to create fence, you compress all that information into this, and then you use this as your handle. So this fence thing is your handle to what was created here. So now fence has some kind of weight substance behind it. It's not a simple variable anymore. It has information encapsulated in it. Briefly, I'll get back to this, but note that we have VK fence create signaled bit. This is to basically start the fence in a signaled state. We're starting the fence in a signal state. I will get back to it. I don't want to get into it right now. I'll get back. So let's continue. So we went through all of this already. This flush command buffer is for staging, the staging buffer and stuff, which I'm not going to cover here, but it also uses a fence, but we're not going to discuss that in this video. All right, now we have our almighty draw call, okay? So the draw call is basically the call that says, hey, GPU, I want you to draw this triangle. Okay, can you draw this triangle? The first thing that the draw call does in regards to fences is that it does this VK wait for fences, okay? And notice that it has the wait fences fence that it's waiting for. So VK wait for fences, you could Google it and the spec will come up from the Kronos group and tell you all about wait for fences, but it's pretty self-explanatory. VK wait for fences. So we're waiting for the previous fence to have been completed. Okay, we're not going to proceed with anything else until the wait fence has been completed, right? This fence has signaled back to the CPU that, hey, we're done drawing, we can now proceed with everything else. All right, so at this point, when we start, once we leave this line and we're starting to proceed with the rest of the script, this wait fences is in a signal state. Now, immediately after it's in a signal state and we can proceed, we do some good housekeeping and we reset the fence to unsignal, right? VK reset fence is unsignal, okay? This is to unsignal the fence. So there's a signaling the fence, unsignaling the fence, right? So we immediately unsignal the fence just so that we don't forget to do it or what have you. Because remember, um, um, we need to make sure our fence is unsignaled so that when it goes back to signaled, we could see a change in state and we could process accordingly. Okay, so I'll play around with this in a minute, but we wait for the fence to say, hey, the GPU has done the draw call and it's now back on the CPU, and the CPU, you know, what have you, we continue with our algorithm. Now, let's proceed. So then now we submit to the graphics queue passing a wait fence. So now we're submitting the new draw to the graphics queue, right? We're submitting the new draw to the graphics queue. But notice that we pass in wait fence again, okay? So this is, it's all one big loop. Wait fence, wait fence, wait fence, okay? But when we pass it in here, we're passing it in an unsignaled state. So remember when I said that it's unsignaled and then we want it to change to signaled. In order for it to change to signal, it has to be, we need to notice or investigate or profile the change, right? If we're doing something and it's already signaled and it puts it back as signal, then we don't, we don't know exactly when it changed from unsignaled to signal because it was always signal before. That is why this reset fence is important, and we'll play around with it, okay? But we wait for the fence, we reset the fence. After we proceed, we reset the fence, and then we do another draw call, but then we put in the wait fences. We in the draw call, we add the wait fences in the unsignaled state. So now what's supposed to happen here is that once the draw call is finished, this is going to change back to signaled again, and then that works well with this line right here, okay? And that's pretty much it, guys. That's the fences. So I'll do it real quick one more time. We create a simple variable called fence. We have a destructor for destroying stuff when we're done because we believe in good housekeeping. We create the fence, right? Right here, we create the fence with a whole bunch of information, but we create the fence, right? We loop through and create the fence. We have this fence variable here. This is staging buffer stuff, which we're not dealing with right now. And then VK wait for fences, wait fences, current buffer. So we wait now for the fence for it to be signaled back that it's done drawing from the previous draw call, and then we proceed. We immediately reset the fence to unsignal. So here, once we pass this line, it's in the signal state. We immediately unsignal it back, right? Because when we're submitting it again, we have to submit it as an unsignaled state. So when this script is done, it's going to signal the fence to say, hey, we have now finished what we need to do. We're going to signal. We're gonna put it as signal, and that's it. Okay. So that's fences for you guys. Synchronization between CPU and GPU. It's not rocket science, but it's close to it though. Not rocket science, but it's close to it. You like that? I know you like that. All right. So let's play around with this. So what I want to do is first of all, I talked about this signal thing. So we start the script off signal. Okay. An important thing in computer science and in engineering and in everything that you do is a thing called initial conditions. Initial condition. Okay. In engineering, in computer science, in everything, one of the hardest things to do is manage initial condition. I'll give you a quick example. Okay, so in the olden days when cars were a little bit less sophisticated, one of the biggest problems people had when they woke up in the morning and wanted to start their car is, would the car start, right? And the whole idea is for a system or for an engine or for a car or any kind of thing to go from an off state to an on state, it generally requires a lot of resources, information, things to come together. What do I mean by that? To have a car that's not started and then to start it, it's a harder process than to keep a car that's already started to stay started. Okay, so if it's already started, it's generally easier for that engine to stay on or to stay started, um, compared to a process where it is off and then you're starting the engine. Okay. And there are many variables. Typically in colder climates, one of the common things is that as soon as winter hits, um, maybe the battery dies, right? Or because of the changing weather and stuff. Remember, you have to have the battery, you have to have ignition, you have to have all kinds of stuff, fuel and everything, right? All of these things have to come together to take an engine from an unstarted state to a started state, and it's generally a harder process than an engine that's already running to keep running. So why do I say this? Back in the olden days when cars were less reliable and it was still being evolved and stuff, um, people who normally had car trouble, let's say they stopped off somewhere to get some food or to go to the pharmacy or what have you. If they had car trouble, they would, and they got the car started and they were driving somewhere, they would go to the place that they were getting food, or they would go to the drive-through or whatever, and the whole thing was keep the car running. Don't turn off the car, because if you turn off the car, you might not be able to turn it back on. Especially in colder climates, or if you had trouble with your car or whatever, they would never want to turn off the car, right? Because if you turn off the car, you might not be able to start it back again. So if it's already running, just keep it running, right? If you had someone else in the car with you, then that's good. Then they could stay in the car while you go into the pharmacy or get food, right? It's the same principle, right? Because turning off the car and then starting on the car, it requires more, and when you turn it off, you can't guarantee that you will turn it back. Okay, so why do I say all this? Here we have an initial condition. The initial condition here is that we're going to submit a draw call, but remember, when we submit the draw call, we have this line here that's saying wait for fence, right? Wait for the fence to be in a signaled position so we could proceed, right? Signaled is on, right? Like an on position. Okay. So this line right here is gonna be waiting for the fence to be signaled. The problem is, if this is the first time the script is running, and there's no previous draw call, there's no previous anything, because it's the first time the script is running. This right here, the fence is going to be in an unsignaled state, right? The fence is going to be in an unsignaled state. So if we don't signal the fence, what's going to happen is that you're going to be stuck here. It's going to wait. It's going to wait and wait and wait and wait and wait and wait and wait. All right? It's going to be waiting. But the problem is that its initial condition, nothing is there to change the status of the fence from unsignaled to signal. So it's just going to wait. All right? So what we're going to do is we are going to, where am I? Come on. All right, so what we're going to do is we're going to play around with it. So let's just run the script as it is normal now. Okay, so running the script as it is normal now, we get a triangle, right? 5,000 FPS, no problem. All right. Okay, so now if we take out the signal piece of it, right? So we're going to create the fence, but we're not going to have it as signal. It's going to be unsignaled. Let's see what happens. 0 FPS. 0 FPS. You ever played a video game where it's 0 FPS? You play a video game where it goes to 0 FPS, that means it's not a good video game, because you're not seeing anything. No frames, nothing, nada. All right? Why is that happening? The reason that's happening is because, oh, all right, close program. Yep, gonna close it. Sorry. The reason that's happening is because the fence is in an unsignaled state, right? We have it in an unsignaled state, which basically means that we're stuck right here. We're stuck right here because this is waiting for the fence to be signaled, but there's nothing to signal it because it's the first time we're running the script. So what we have to do is make the fence in a signal state, right? But when we put it back into signal state, we're going to see that the script runs and we're at 5,300 FPS. Understood now? Because now the fence is signal. So we start off with signal. So because we start off with signal, we run right through this line, right? We pass this line because it's signal now. So we're good. It's signal, so we could proceed with everything else, right? I mean, obviously after this line, it does it back to unsignaled, and then it submits it with the unsignaled, and then it's signaled again, and all that, right? So we know that game. All right. So so that's that. Now the thing about it, what we also want to play around with is this unsignaled, how to changing it from signal to unsignaled. Now it's kind of strange. I mean, the thing about it is that there's no like, you see how you have this flag here. You see how you have this flag here for signal. Like, you could flag the fence as signal. So when you push all the information for the fence, it basically has this flag for signal. There's no like counter flag. Like, there's no like unsignaled bit thing, right? I don't know if you guys at Chronos wanna make like a flag for unsignal, but I guess if you create the flag and you don't have this thing here, then that just means that it's unsignal. You know, it would have been nice to like have an explicit flag for unsignal, right? So if you like comment this out or whatever, I guess it would just, it's automatically defaulted to a fence that's created in the unsignal state. Okay, that's the Chronos, that's the Vulkan API spec. You know, they decide what they want to decide. Okay, but let's play some games. Okay, so we create the fence in a signal state. What I want to do is I want to use this reset fences thing. I want to use this reset thing, and I want to see what happens when I want to see what happens when I basically, we create the fence with the signal state, right? But then I want to reset it to unsignal, right? So I'm just doing this to basically see if my line of logic is correct. So we create the fence signal, but then I want to reset it to unsignal. Now what should happen, what we're betting that should happen, is it's almost as if we had created the fence in an unsignal state, right? But we're doing it with VK reset fences. Instead of just commenting this out, we're doing it with VK reset fences. So we're betting that we get the same behavior as if we had commented this out, right? And we actually do. As you can see here, 0 FPS, okay? So we're not gonna spend too much time with this. We're just gonna close that out, all right? So you guys get the drift now, right? We could create the fence in a signal state using this, and we could reset it to unsignal. Now let's play a game further with it. Let's redo, we're gonna redo the fence now, but we're gonna do it with signal, right? So we're kind of overriding and stuff and whatever. But if I'm a betting man, I'll bet that it's gonna basically act like normal, right? It's gonna basically act like how the script originally ran. Okay, so we're gonna do that, and basically now it should be a triangle again, and that makes sense. Okay, that makes sense because we flag the fence as signal, we create the fence as signal, we reset it to unsignal, but then we recreate the fence again in the signal state because it still inherits this flag right here. And as suspected, that's what happened. All right, so this is all part of the process, guys, of learning Vulkan, is that, you know, work with running code. and get stuff, learn. So we know now how to signal a flag. We know how now how to signal something. We could signal it with this flag here, and then uh right, we could signal with the flag here, create the fence, but then we also know how to unsignal it with the reset fence, right? um I guess you could also create another fence without this flag, and if you don't have this thing here, this flag here, then it's assumed to be in an unsignal state. Okay, and that's fences, guys. It's not rocket science, but it's close to it, right? But we're learning. So that's fences for you. Now there is another use. They do use the fence in another situation with the command buffer, and like with the uh with the staging buffer and all that stuff, but I don't want to get into that. That's like a whole other thing and what have you. But just remember, anytime in Vulkan you see fences or mention of fences, we're talking about CPU to GPU synchronization. One process on the CPU, which in our case it's submitting a draw call, and then another process on the GPU, which is drawing, you know, executing the draw call, drawing something, in our case, a triangle. And then once it's finished drawing, you communicate back to the CPU that, hey, I've finished drawing, let's proceed. And that's it, guys. So I encourage you, get a group of your friends together. You all get the tutorials, work through Vulkan. These things take time. If you play video games, that's good, but also learn some computer graphics in the process, right? So you understand what's happening in the background. Check out the whiteboard, which is 2 videos ago, which diagrams out a whole bunch of this stuff. I'm pretty much finished with the fences. I'm pretty much finished with the fences and semaphores discussion. I'm probably gonna move on to something else. I don't really want to say right now because things are subject to change. But definitely, guys, learn some computer graphics. Computer graphics isn't just for video games. It's for, well, now we have Apple Visual Pro device, whatever, right? We have the Meta device, right? Meta has their own virtual reality stuff. Um, Scientific visualization, data visualization. In real estate, they do a lot of computer graphics for mapping out the visuals of construction, of new homes, of things of that, especially high end real estate. So you want to see the thing before the actual thing is built. There are a million things you could do if you know how to put pixels on a screen, if you know computer graphics, right? It could open up your career. The world is changing a lot, so we don't know how things are going to change, but we do know that things are going to go digital, and there's going to be a need for just basic programming skills. And if you could program something that creates pixels on the screen, that's very powerful because everyone can appreciate a visual thing. All right, so tell your friends, watch the videos, subscribe to the channel, get tutorial number 1, get tutorial number 13. You could also get the series, which basically walks you through creating a triangle. And that's it, guys. So thanks for watching, and